So this is for physics second semester algebra based. We're talking about chapter 23. This is section 4 through section 7. Hopefully we're going to do all of it in this video, and I'm not going to cut it up, but let's see how we do. So section 4, we're going to talk about eddy currents and magnetic damping of movement. We'll talk about it, so you'll see here in a second what we're talking about there. Then we're going to talk about electric generators and motors and the differences. And then section 6 is the back EMF of a motor. And then section 7 is all about transformers. So they're more than meet the eye. So that's all I have to say about that. Motion EMF, let's do that. Let's get into it. So remember, for emotional EMF, we can have a whole bunch of things that change in an EMF, right? We can have the B field can change, the area can change, or the cosine of the angle can change. But these are the only two that are motional, okay? So these are motional EMF. Wow, this is really working well. Motional EMF, okay? So let's say we have a conductor and it's moving through a B field like on a pendulum, okay? So there's a sheet, metal, I don't know, steel or aluminum, it doesn't matter, some metal conductive thing that is going to swing through this B field. And you can see that the B field is pointing into the page, and this metal piece is going to swing through that B field from one side to the other. It's not a loop, okay? It's a full-on sheet, all right? So it's solid, right? But it's thin, okay? So it's this thin thing that is completely solid, and it's going to slide through this B field. Now, the motional EMF causes current in the conducting plate of metal, all right? So what happens is as it's going in, these little currents are created. Currents of electricity get created because of this motional EMF. We call those currents eddies, okay? And eddies are just like you think they are. They're the same thing that when you see a creek or a river or whatever, and there are whirlpools in the river, those are called eddies because they just kind of swirl around. Well, these things swirl around, the current swirls around inside the plate. And basically what's happening is there's kinetic energy, right? We've got kinetic energy from the actual movement of this plate, all right? Because 1/2 mv squared, that's the kinetic energy. So it's moving through with some velocity v, and that v is going to carry it through, and it's going to go, oh yeah, hey, I got all this extra energy, and then entropy comes along and says, oh, well, hey, wait a minute. I got to take some of that money away from you, like taxes. It's like paying your taxes. And so it slows down. There's actually a force that gets created that slows this thing down, okay? And it's very, it's well known. This is a well-known thing. The energy gets released as eddy currents, and they're looping through the conductor, and so that reduces the kinetic energy. So it reduces the kinetic energy. They say it reduces the mechanical energy. Your total mechanical energy is equal to this plus this, right? But the potential energy comes from gravity. So the height of the thing might reduce because it has less kinetic energy, but unless it's moving, there's no stealing. So it can't steal from the potential energy. It's only stealing from the kinetic energy. So it can't happen, right? Unless it's stealing as the thing is moving, which in other words means it has to be stealing from the kinetic energy, which steals from the total mechanical energy. All right, so as soon as the V increases through the B field range, then I or I, depending on which way it's going through, are created. So there's these two different loop eyes, little eddies that can be created. Okay, well, that's magnetic dampening, taking energy out of the system. But we're going to talk about exactly where that energy goes and how the force does the magnetic dampening. So we're going to move from left to right. So we're going to start over here with this number 1, and then we're going to end up over here with this number 5. And that didn't work. Okay, so starting from 1, it hasn't entered the B field yet. So what happens as it goes in is nothing. It's not doing anything here. So there's no loss here. Okay? But gradually it's going to get to number 2. So here's number 2. And it's starting to enter in. So what's happening? Well, the flux, our magnetic flux, is going to increase, okay, through our area, through the area of this thing. Now, it's not a loop, it's a solid piece, right? So little eddies are going to get created inside this thing. So it's going in, and as it enters the B field area, it's going to start losing due to this EMF that gets created. And it's increasing as it enters. So what happens is, if it's increasing, then we need to figure out a way to make, or the loops figure out a way to make that increase a decrease, or oppose the increase, right? So they have to create a current that's going to oppose the increase. So how do they do that? Well, they're going to do, if it's increasing, so it's into the page, our B field is into the page, and it's increasing, the flux is increasing, so then a current has to be created that goes in the opposite direction. So it wants to create a B field that comes at us, out of the page. So how does it do that? Well, to create a current that comes toward us, it has to create a current loop like this. Okay, so current loops, as it's going in, get created going in that direction. So if we're looking at just this side of our plate, then our current is going up on that side of the plate. And we want to figure out what the force is. And so this is the equation. I'm just taking Lorenz's law and I'm turning it into this. Our force is I cross B, and then to get the right amount, you have to multiply by L, whatever the L is, the length. So I cross B, fine. We do our right-hand rule, so we put our fingers up the page, our palm facing toward us, and we curl our fingers towards the B field. Oh, our palm has to go down, our eye goes up, so our hand is sticking our fingers up to the top of the page, our palm goes down because that's where the B field is, and then our thumb points to the left. So our force in this case is going to be in this direction. Okay, now look, it's sliding in with a velocity going in this direction, and our force is opposing it. Notice that? Interesting, right? Okay, so that is what we call damping, all right? So now it's totally in. We're in stage 3 here. Okay, we're all the way inside this the B field area. Nothing is happening. Why is there nothing happening? Because there's no change in the flux. The flux is staying still, no change in flux, no EMF. Gradually, we start to roll out of our B field, and again, the flux is decreasing. So what happens? Well, the current wants to make the decreasing flux increase, so it has to add to an already into the page. So it needs to make B field look like this. That's not working. Into the page B field. And in order to do that, then it has to do a loop that's going to go into the page. How is that loop going to look? It's going to look like this. And again, the current is going up on the left side of our plate. So we have our up current going on the upside of the plate. We curl it to the down. So we have our palm facing into the page. We have our fingers going along the current. We bend them toward the downside of the B field, and then our thumb points in the direction of the force. And again, at this point, we've got a force that's slowing us down. Okay, then once we're out in number 5, we're completely out, and again, we're not in a B field, so there's no flux changing. This whole thing is gonna swing over from 1 to 5, and then it's gonna swing back from 5 back to 1. So it's gonna do the same thing, only now it's gonna create the opposite. So the B field doesn't change, but the current that happens, that gets developed from the E field, is this current as it's going back in from the other side. So we're going to do our, which way does the force point? Well, keep in mind it's swinging this way. All right, so we've got our eye. I'm going to put my eye, my fingers pointing toward myself, my right hand pointing towards myself. I've got the B field down, so I'm going to curve down towards the B field, and I'll notice that my force is just like this to the right, opposing my velocity, therefore slowing me down. That's a deceleration. And of course, if you do the same thing on the way out, the current is going to be still going down the page on the right side of the plate, and again we're going to end up with force like this. So that's how it works, and I know it's kind of a little complicated, but you're going to have to wrestle with it and figure it out, and there will be questions on this, so make sure you kind of understand how that's happening. Okay, so what happens if we cut slots out of the metal sheet? Well, that makes it harder for these eddy currents to develop, right? Because an eddy current now has to be small. It has to go in here like this, right? Our eddy currents have to be smaller, and therefore we lose less energy to the eddy currents. So the entropy can't take as much energy out of the system. So the nice thing is you cut these slots into these things, and lo and behold, you're saving energy. And a whole plate will have more force opposing it. And if you want to minimize it, then you cut all of it out of the inside, and then you just have a wire left, right? So we just have the wire left, and then at that point, you can see that this is what happens if we're sliding in to the B field, and this is what happens if we're sliding back through the B field. So either way, we end up with our force, and I don't know why my cross product got a circle around it. I'm not sure how that happened. But there's our cross product, and I cross B gives us our F. Okay, and then you just multiply by the length that's happening here, and you've got yourself the exact force. All right, so what did we use? We used Faraday's law to do all that. Faraday's law is awesome. If the V is fast, when then the I is large, and when V is slow, then the I gets, it's not as big, it's smaller. So how do we, this is why Faraday's law is so good, because if V goes up, our phi goes up, our EMF has gone up, our current goes up, and our damping goes up. If V is, dropping or slowing down, then our phi slows down, our EMF slows down, our current gets smaller, and our force gets smaller. So this is really a cool thing that we can use, and damping is definitely something that we have put to use many different ways, and keep in mind, all of this comes with a constant B field. Okay, so we could use a magnet. You could just have a simple magnet that will do all of these things for you. So applications for this. Well, it's tricky, but you can make, how we measure the masses in class? You can have very precise mass measurements using this. It gets really precise because you can go down to microamps and that kind of stuff and get the exact amount of mass causing these things to happen. So that's quite a good way to use it. But one of the best ones I like is this one right here. It's easy to see. So when you're sorting trash, I don't know if you've seen those trash facilities where they put the trash on a elevator, a ramp with a treadmill thing, and they just put all the trash on there, and then there's a magnet along the way, and as they go through the magnet, all the metals get separated out, right? They get a force pushed onto them, and it pushes, because the magnet's there, it pushes those metals to the side. So another thing is a metal detector. I don't know if anybody's walked around with a metal detector, but it's kind of fun to do. I think I made one. I had no idea what I was doing in 8th grade, and I made one. But anyway, they can tell. They monitor their own EMF or the current or however they do it in all the loops that they have, and then when metal gets close, the flux changes, and that changes the I or the EMF, and then the detector beeps, and it tells you, oh, you've got a lovely gold doubloon in the sand, and everybody's happy and they scream and run home, and they got millions of dollars now. Okay, so let's talk about electric generators again. Electric generators, I've done a thing here where I've got this water wheel, and let's say water's coming down, in a fairly fast situation. There's like a little falls or whatever, and it's very quaint. And this wheel gets turned because the water runs over the wheel and turns it and causes the wheel to turn, say like this, okay, with some omega. So here's our wheel, and the water's going over it like this, and it's turning the wheel. And there's magnets, okay? So we've got our magnet here, and we've got our magnet here, and we've got our loop in the middle, and the loop gets turned by the wheel. And what that does is it generates current in the loop. And then that current ends up going here, and we can notice the current with an ammeter, okay? Or we can store the current. We could hook it up to a battery and actually charge up a battery, or run something with it. We could do all kinds of stuff, okay? So the water wheel is a really, really cool way to, like if you went back in time and you had to create electricity, this might be a way to do it. Find some lodestones somewhere, and you could do it. So, example 23.3 in the book. Good luck going back in time, by the way. I'm telling you, it's this example in the book. So if you really want to go back and go through it, definitely do that. So we've got a water wheel loop. Our loop is going to rotate from A to B. Okay, so what's it doing? It's starting out at theta A at 0 degrees, and then it's going all the way to theta B at 90 degrees. And it does so in this amount of time. So I'm just rewriting that. And there's in our loops, there's 200 loops. Okay, so I only drew one in my water wheel, but we have 200 of them. Our average radius of the loops is this. Okay, so there's a whole bunch of loops, and they all have different, a little bit different radius, but there's an average radius for this whole thing. Okay, so the average is really what we want, because some of them are going to have more and some of them are going to have less, and we really just want our average. Okay, so our average is 0.05 meters. The B field, constant. Okay, this is a constant and very uniform. Okay, so what is the EMF average produced? Well, we're going to start again with Faraday's law. Okay, so very important. And we're going to figure out what our magnetic flux is. So our magnetic flux, the area isn't changing. Only the angle is changing. So the magnetic field isn't changing. So we're going to use this right here and figure out what's happening. And if we take the cosine of 90 degrees, that's this. Cosine of 90 degrees is 0. The cosine of 0 is 1, but we've got our minus sign here. So that means that minus 1 times BA is equal to our phi, our delta phi, our magnetic flux, change in magnetic flux. So what is our area? Well, that's not too hard to figure out. Area is equal to pi r squared. So we've got our pi r squared happening, and easy enough, we can figure out that this is our area. So now we can do everything. And we're going to put our n is 200. We've got our negative sign. N is 200, but then we also have minus BA. Here's the B, minus B, and then there's our area. And we're going to divide all of that by the amount of time. And when we do that, the two negative signs cancel out, and we're left with 131 volts. So the water wheel is producing a voltage, actually, that looks pretty good. It could pass for voltage at somebody's house, because we normally use about 120 volts. So that's a pretty, solid thing to do. But I want to know, what is the EMF at any point in the turn, right? Not just from 0 to pi over 2 to 90 degrees. I want to know any part of the turn. So I am skipping how we get this. If you want to learn about how this equation comes about, please read the book. And I'm not skipping it for any reason other than I think the takeaway is all you really need. Okay? There's reasons why it's this, but look, I mean, it's the same thing. Our EMF is the number of things times the number of turns times our B field times our area, and then we're going to be multiplying by the omega, that is how fast that it's turning, its angular velocity, okay, times the sine of the angular velocity times time. So what is omega again? Of course, that is our angular velocity, and that's really just the amount of radians per second. So we've got our number of loops, we've got our B field, we've got our area of the loops. All those things make sense, and now we just need to have this omega times the sine of omega t. So we went from here to here in this amount of time. So should we be able to figure out what our omega is? Yes. But we want radians. So 0 radians is 0 degrees. Pi over 2 radians is 90 degrees. So we're going to do pi over 2. We went from pi over 2 to 0, or 0 to pi over 2, whatever, but this is the distance we went. And we did it in this many seconds. So pi over 2 is equal to pi, and then there's our 2, and then there's the seconds. That gives us an omega that is equal to 104.72 radians per second. All right, that's a lot. If you divide that by 2 pi, you'll find out how many revolutions that is per second. And that's a lot of revolutions per second. So I have a feeling that our old-fashioned water wheel is not as old-fashioned as we'd like to think it is. That's a very quick speed. I've never seen a water wheel in the movies do that, right? So very fast. But it could be a turbine or something like that, or a turbine in a generator or something. So, but let's figure out what what is our EMF. Okay, so let's do that. So we're going to plug in all those numbers. We've got our 200 for the number of turns. We've got our B field. We've got our area. We've got our speeding omega. And then we're multiplying all of that times the sine of omega t. Right. So that's all these things. But we want the maximum, okay? And that happens every time sine of omega t equals 1. That means omega t is equal to pi over 2. So all I'm going to do is figure out what is the max. Okay, so this is our max, and that's 205.5 volts, or we could say EMF max is equal to 206 if we round up volts. Right, so keeping in all that in mind, if E max is this, that's our E max, epsilon max, then we just substitute that in here, and now we've got our EMF as a function of time. It's our E max times the sine of omega t. And that's really it. Now we have to remember, I want you guys to remember a few things that I know you guys know this stuff, but I want you to bring it back to memory. Omega is equal to 2 pi times your frequency. Frequency is how many times per second, so it's called hertz, which is equal to 1 over a second. That's the units. That's how many times it does its revolutions or cycles. The frequency and the period of rotation are inversely proportional. Okay, so the period of the rotations is 1 over f, or f is equal to 1 over t, however you want to look at that. So omega is 2 pi over t. That means that our period of revolutions is t equals 2 pi over omega. So what does that look like? In the end, we have a sine wave. So the sine wave starts out at 0 at t equals 0, and it goes up to the E max, our EMF max. It goes down to the EMF max on the min side, but on the negative side, and then back up and down and back up and down. And every time it gets back to here, that's how long it takes for one period. Okay, there's our fourth period right there. Okay, so we want current to flow only in one direction, right? It's no fun if you do something and then half a period later it's X'd out, because here you're working here, you're happy, all your current is working in the right direction, and then everything that you just did is reversed because your current flipped around and everything. What a bummer. So we use this thing called a split ring, okay, on our motors. And what that is, so here's our loop up here. We're going to have some loop going up in here through a magnetic field. And then it spits out some current. And this side, let's say our current comes down here. And once the current is coming down on that side, all of our loops here like this, current comes down on that side, it can send the current here, okay? And then as this thing spins around, next thing you know, this piece right here is over here and it's touching that guy. These are brushes. These are called brushes. And you've seen the brushes. They were on the, not Erling, on the, oh gosh, what's the name of that machine we were generating sparks with? Anyway, those are brushes. So those brushes rub on these two split rings. And once we get this side over to that split ring, guess what? This whole thing has spun around inside the magnetic field, and it's causing the current to come down on this side now. Well, that's perfect, because it's then over here and it's going to continue to send our current down on that side. So it's a very elegant way to keep current flowing. And then it would generate an EMF kind of like this, where it'll always get back up to our E max, but it bounces. So instead of basically we're just flipping. Every time it goes negative, we make it positive, like this. And that's what these are. Positive, positive, positive. Now we have two positives to make one period. Okay, so 4 positives makes 2 periods, and so on. Now there are other ways to do that, of course. There's a digital way to do it, and that means using a diode. Oh, sorry. That means using this diode here. A diode looks like this in a circuit. And what that means, this diode is saying, oh, I'm only going to allow current to go in one direction. Okay, and that alone pretty much solves a lot of the problems that people had in the past, but they didn't know how to make diodes back in the day. So we've developed diodes in the 60s, I think, and ever since, life has been just better for us. Everybody's happier. Okay. So let's get back to electric motors and electric generators. They're the same thing, only one goes one way and the other goes the other way. All right, so we have motors that have electrical energy stored in a battery or a capacitor or something, and they send that energy into our motor. Here's our motor. And then it spits out mechanical energy. Well, a generator takes the mechanical energy, like the water wheel that's being spun, and it takes that energy into the generator. I'm just going to put GEN here. And it spits out electrical energy. So one has the things going one direction. The electric energy turns everything into kinetic energy, typically. It's kinetic energy. And then this guy takes our kinetic energy and moves it into electrical energy. So we could store it in a battery or a capacitor. Okay? Batteries or capacitors. So that's it. It's the same thing running in reverse. It's pretty cool. Well, and like I said earlier, it's the potential energy isn't really affected a whole bunch. It's really the kinetic energy of movement that's giving us this thing. So we could look at a motor. Let's look at a motor. And this motor has some axis right down the middle, and it's spinning with some omega through this B field, and it's charging up a battery. And we pass the current through the loops from the battery because this is a motor and we want it to spin so that we can turn tires on our car, or who knows what we're doing. Maybe we're running a blender, or I don't know. So we have this motor and it's spinning things, and it takes energy from the battery as our EMF, and it spins around and causes everything to turn. Okay. But here's the but. This changes the flux. Okay, so change in flux. What does that mean? That means delta flux. So an EMF gets produced that is going to oppose our battery doing this thing in the first place, which is kind of against kind of what we want to do. The good part is, well, let's just keep going with the bad part. It's Lenz's law that's telling us that it's going to oppose our battery that's driving the motor, and so that's kind of bad, right? And we call the secondary EMF, we call it a back EMF. Now it only applies to motors, okay? So because we're running the current through our motor as a battery. If we're just letting nature spin this thing around, it doesn't have, it's doing what it wants to do, and it's charging up the battery for us. But since we're using it as a motor, it gives us this back EMF. So back EMF completely comes from motors only. So you can think about it a little bit. Think about how a generator is not going to generate a back EMF because you're taking the mechanical energy and you're shoving it straight into a battery. But this way we're taking current, we're producing this thing, and it's giving us a back EMF, right? So the circuit kind of would look like this. We've got our battery. All right, we'll close the circuit, and the battery is running through our load, whatever the thing is doing. You know, maybe it's a microwave or it's spinning something. Who knows what it's doing? And then it generates a back EMF, also EMF B if you want. If the motor is spinning too fast, then the EMF B gets larger than the V battery, and therefore it will start charging back up the battery. Okay, so that can happen. If it gets out of control, that can happen. Of course, at that point, you're no longer producing an acceleration. You're no longer getting your kinetic energy out of it. You're probably slowing down, actually. So that's not, it's not super helpful, but it's a thing that happens, and I want you guys to know about it because there's a question about back EMF. Okay, so this last bit here is on transformers. Let's go for it. We've got section 23.7, the symbol for a transformer. And I don't know if I wrote this down for you guys already, but we've got a voltage inside. This is our voltage inside. This is our voltage outside. And the output is the V out, right? We've got some input voltage and an output voltage. So that means that there's some current that goes in and out of this thing. So we'd have current that our V in has current I in, and then I in comes back out through that circuit. But on the other side of the circuit, it's got I out going with V out, okay? Now, one important thing is transformers only work with AC power sources, all right? So it only works with AC. You can't transform DC. You can, but it's a lot harder to do, and transformers are inexpensive. So we like to use AC. Everybody wants AC to do these things. All right, so here's how it works. This is an example of what happens. Pretend there's a generator. It could be a wind generator or a steam plant, or like coal. A steam plant is just coal burning, heating up water, turning it into steam, spinning a turbine. A hydroelectric dam has water running past a turbine. All these things have turbines, okay? The wind causes a turbine to spin. All these things are spinning electric magnetic motors, or generators, right? Not motors, they're motors in reverse, so it's a generator. Generators, you can go to General Electric and buy motors, and they all produce about 440 volts. I don't know. Maybe some do more than that. I don't know. But, so what do you got to do? You don't live next to, let's see, the Hoover Dam, for instance. You don't live next to Hoover Dam, but that's where the generator is. So what do you got to do? Well, you got to step up. You have a step-up transformer here. We step it up to from 440 volts to 10,000 volts. And then we go, oh, well, you know what? We still have to get all that energy from here to Los Angeles. And that's a long distance, right? So we've got to get a really high voltage. So we step it up again. We get this really high voltage so we don't lose any power from the Hoover Dam out to wherever it is, your house. Near your house, there's some local power station. You guys have seen them around. You'll see them. You don't really know what they are, but they're just these big, huge areas that have a bunch of transformers in them. That's really all they have. So there's this station in the neighborhood somewhere around where you live. There's a power station where it steps down all the voltages and steps it back down to about 10,000 or 5,000, somewhere in there. Then it can go a few miles from that station to a place very near your home, outside your home, in fact. Okay? Right outside your home, there's a step down that steps it down from either 5,000 or 10,000 to 240 volts. That's what it is when it enters your home, and it goes into your house, and in that one, you know where the breaker box is? Well, inside that breaker box, it splits that 240 volts in half, and it sends half to one side of the house and half to the other side of the house for your 120 volts. And it's a pretty elegant system, actually. It works really well and very straightforward. So let's talk a little bit about how transformers work. So a transformer works with some core on the inside, and the core is made of iron or some other ferromagnetic material, and it's laminated. Why is it laminated? We just talked about why. It has to have layers, and it has glue that is insulating in between each of the layers so that the eddy currents don't get created and go like this. They can't go like this now, okay? They have to only go like this through the through each of the laminations. So there's glue in between each of these things. There's glue in there, and that glue keeps them from going sideways. This way is okay. We're okay with this happening, but we're not okay with this happening. All right? So that's why they put the insulating glue in between the different layers. That keeps the eddy currents down and not allowing them to go sideways. Okay, so all of that, let's get rid of some of these. There. Now, so our the N in, okay? Also, listen, the book calls these things, this is the primary, and we'd have N primary, and we'd have current primary on the inside, and then on the outside, we'd have V secondary, N secondary, and I secondary. Well, that's dumb. Just call it in and out, and then you know what you're working with. You could call them 1 and 2, but is 1 in or 2 in? Nobody knows. Why don't you just call it in and out, and then you're done? So anyway, that's my thing. That's what I would do, and that's what I'm going to do. And if you want to change it to P and S and all that other stuff, that's fine. Go ahead. All right. So we've got N in. That's the number of loops on the in side. So how many loops do we have here? 1, 2, 3, 4, 5, 6, 7. So there's N in is equal to 7 loops. Okay? Now we go to the other side. What is N out? Well, good luck counting that. But it's more, right? It's definitely more. So N out is greater than N in. And it's not just a little bit greater, it might be 3 times as many, right? So that's good. So here's what happens. This is our EMF, okay? And the EMF is equal to the number of coils times the delta flux divided by delta time. But both on the in side of the transformer and the outside of the transformer, both of those have the same flux divided by time. But the N out and N in are different. The V out and the VN then have to be different. So this is what we call the transformer equation. V out over V in is equal to N out over N in. Okay? And all I did was I just rewrote this, okay? Because these things are equal, and that means this equals that, and so I just rewrote it. So we have ratios, okay, of N in and N out, and V out and V in. So N out in our case above is more than N in, right? So that means that V out has to be more than V in. And so since that's the case, this is a step up transformer, all right? When V out is greater than V in, it's step up. If we flip the whole thing around, we just pick up our transformer, unhook one side and hook it up to the other side and vice versa. Then V out is less than V in, and this is called a step down transformer. And then, of course, N out is less than N in, right? So we just flipped it all around. So not only are transformers inexpensive, okay, that's the main reason we use them so much in AC and all of that, but they also hardly lose any power as they're transforming from one to another. So the R transformer, the resistance in the transformer is really small, okay? It's a very tiny part. We don't lose any power there. So our power that goes in is the same as the power that comes out. So this is another equation that we can get. V in times I in is going to be equal to V out times I out, right? Here. And that's yet another equation. It's not the transformer equation, but it's very similar to it. And because of the transformer equation, we can take our I in over I out, that equals V out over V in. And otherwise, we could use the transformer equation to rewrite that as I in over I out is equal to the number of turns on the outside versus divided by the number of turns on the inside. So let's do an example. The examples get pretty easy. So at the hospital, X-ray machine, it plugs into a wall, right? So it's got this as an input, 120 volts. But it needs this as an output to produce X-rays, okay? So it's got to crank it up, right? And the number of loops on the inside is 50. Well, that means that we've got to have a lot of loops on the outside. So we're going to figure out how much that is. We also know that the current going in is 10 amps, okay? So what is N out? Well, we can easily do the transformer equation and get that. And we're going to plug in those numbers, and N out is equal to 41,700 turns. Okay, so that's a lot, right? You have 50 on one side and 41,000 on the other side. So that's a lot. But what is the current out? All right, so that's a good question. We could use either one of those equations to do it. And either way, Either way, you're going to come out with this answer. This way, I think, is the number of, no, that's the volts, 120 volts in 100,000 volts out at 10 amps. I out, we could do the same thing with the number of turns. This is our 50 turns on the inside, and this is our 41,700 turns on the outside, and then times our amps. Either way, you're going to get this as your answer. Okay, so you can try it. Plug it into your calculator and make sure that works out. All right, so now example 23.6. This is a step down transformer. So you've got some battery charger at home. All right, you can charge up batteries with it. It's very easy. You've got 15 volts as the output to charge up these batteries. The input from the wall, again, is your 120 volts. So you have a transformer that has an in, and the number of loops on the inside is 200 loops. How many loops do you need on the outside? So on the outside, we're just going to do the transformer equation. Simple ratio times our 200 loops gives us 25. So we start off with 25 on one side, we start with 200 on one side, we end up with 25 on the other side. That steps it down, and we go from 120 volts to 15. Now, if I out needs to be 16 amps, okay, so that's a lot of amps. We need that many coming out. So what do? What does IN have to be? So we calculate this IN, and it doesn't matter which one we use. We can use N out over N in, standard. Then we take this ratio, multiply it by 16, and we get our 2 amps. Very nice. So good job, guys. Hope that went well for you. Ask me any questions, email me, and hopefully you'll have everything you need to do your homeworks. Thank you.